The third part of Chapter 8 is on sections 8.5 and 8.6, so you can go to page 204, please. If you look at the outcomes in a study guide, you should be able to understand and calculate conditional probabilities and understand and apply the concepts of independence. Here, you should be able to prove that two events are independent, or you should be able to use the formulas in calculating probabilities. Then you should also be able to understand and apply the 4 laws of probability. For conditional probabilities, we calculate the probability that some event will occur given that another event has already occurred. So, if you want to calculate the probability of event A given that event B has already occurred, you will take the probability of the intersection of A and B and you divide it by the probability of the given part, which is the probability of B. So our relevant sample space will now be event B instead of the whole sample space. For example, suppose that you toss a balanced die. That means that all your outcomes in your sample space will be 1, 2, 3 up to 6, and then they want you to calculate the probability of obtaining a 1 given that an odd number was obtained. So that means that we can define event A as observing a 1 and B as observing an odd number. That means that our outcome in event A will only be a 1 and the outcomes in event B will be a 1, 3 or 5. The probability of event B will then be 3 over 6 or a half. And if we look at the intersection of A and B, they have one outcome in common, which is a 1. So the probability of A and B will be 1 over 6. Then our conditional probability of A given B will be 1 over 6 divided by a half, so the probability will be 0.333. Before we look at the formulas for independent events, let's just look at a bit of background so that you can understand the concept of independent and dependent events. If events are dependent on each other, it means that that event can be affected by previous events. So these events depend on what happened before. So that means that the chances or probability that that event will happen will change. For example, let's say that we have a bag containing 5 marbles. 2 of the marbles are blue and 3 of the marbles are red. Your chance of drawing a blue marble on the first draw will be 2 over 5. But if you do not replace that first marble and you draw another marble, then your chance of drawing a blue marble will change. If you had a red marble on the first draw, the chance of drawing a blue marble in the second draw will be 2 in 4. But if you had a blue marble on the first draw, then your chance of getting a blue ball on the second draw will change to 1 over 4. However, when events are independent, they are not affected by previous events. So these events do not depend on what happened before. So the chance or the probability that an event will happen will not change. For example, let's say that you toss a coin 3 times and it comes up heads all 3 times. What is the chance that the next toss will also be a head? Well, the chance will simply stay 0.5 like any other toss of the coin, because each coin toss is an isolated event. So the coin can't remember what outcome it had before. So what it did in the past does not affect our current toss. So we can prove that two events A and B are independent in the following ways. The probability of A given B will simply be equal to the probability of A, which implies that event B didn't affect event A. Or the probability of B given A will simply be equal to the probability of B, so event B was not affected by event A. And the probability of A and B will be equal to the probability of A times the probability of B. Otherwise, if these conditions does not hold, then it means that the events will be dependent. For example, let's say that we toss a single die. So the outcomes in our sample space will be 1, 2, up to 6, and we define the following events. Event A, we observe an odd number. That means that the outcomes in event A will be 1, 3, or 5. So our probability that event A will occur will be 3 over 6 or a half. Event B is defined as observing an even number. So the outcomes in B will be 2, 4, and 6, and the probability will also be 3 over 6 or a half. And event C is defined as observing a 1 or a 2, so the outcomes in C will be 1 and 2, and the probability of C will then be 2 over 6 or a third. Now in question A they ask you, are events A and B independent events? So the intersection of A and B will be a null set because event A and event B had no outcomes in common. So the probability of that intersection of A and B will be 0. But if you multiply the probability of A and the probability of B, you will get a fourth. So that means that events A and B are not independent, since the probability of the intersection is not equal to the probability of A times the probability of B. You could also prove this by the conditional probability. So either one that you prefer. In question B, they ask you, are A and C independent events? A and C had one outcome in common, which was a 1. So the probability of that intersection will be 1 over 6. If you multiply the probability of A and the probability of C, you will get 1 over 6 as well. So that means that A and C will be independent because the probability of the intersection is indeed equal to the probability of A times the probability of C. In example 8.18, they tell you that 3 brands of coffee, X, Y, and Z, are to be ranked according to taste by a judge. So if we draw a tree diagram, we can get the outcomes in our sample space, because we are going to need that to calculate the probabilities. So any of the 3 brands can be ranked first, but then you will only have 2 options for the second ranking, since the same brand can't be ranked first and second, and then for the third rank you will only have 1 option each time. So we have 6 possible outcomes in total in our sample space. Then they define the events as follows. A is the event that brand X is preferred to Y. That means that we will look at all the outcomes where X was in front of Y. So our probability of A will be 3 over 6 or a half. Event B is defined as brand X is ranked best. So there you will look at all the outcomes where X was in the first position, and the probability of B will then be 2 over 6 or 1/3. Then event C was defined as brand X is ranked second best. So there we will look at all the outcomes where X was in the second position, and the probability of event C will be 2 over 6 or 1/3. And then lastly, event D was defined as brand X is ranked third best. So there we will look at all the outcomes where X was in the third position, and that probability will also be 2 over 6 or 1/3. Then they ask you, are event A independent of events B, C, and D? If we look at the intersection of events A and B, they had these outcomes in common. So that means the probability of that intersection will be 2 over 6 or 1/3. But if you multiply the probability of A and the probability of B, you will get 1 over 6. So that means that A and B are not independent events because the probability of the intersection is not equal to the probability of A times the probability of B. If you look at the intersection of A and C, they will have 1 outcome in common. So the probability of that intersection will be 1 over 6, And if you multiply the probability of A and the probability of C, it will also be 1 over 6. So A and C will be independent events because the probability of the intersection will be equal to the probability of A times the probability of C. If you look at the intersection of A and D, they will have no outcomes in common. So that intersection will be a null or an empty set. So the probability will be 0. But if you multiply the probability of A and the probability of D, you will have 1 over 6. So that means that A and D will not be independent, since the probability of that intersection will not be equal to the probability of A times the probability of D. The laws of probability are given on page 207, and the first law is the additive law, and the additive law is applicable to mutually exclusive events. If you think back of part 1, we said mutually exclusive events are events that cannot happen at the same time, so they will have no outcomes in common. If that is the case, then the probability of the union of events A and B will simply be the probability of A plus the probability of B. And it doesn't matter how many events you have, the union of the probability of all the different events will simply be the sum of the probabilities of those events. For example, continuing from example 8.5, where we were interested in the probability of obtaining a total of 7 or 11 when rolling a pair of fair dice, they now ask you, what is the probability of getting a 7 or 11? Now, these two events will be mutually exclusive because you can't get a total of 7 and a total of 11 at the same time. So we can define event A as getting a total of 7. So the probability will be 6 over 36 because our sample space had 36 outcomes in total. And for event A, we will look at all these outcomes in green. Then event B, we can define as a total of 11. So we are going to consider these two outcomes for event B. So the probability of event B will be 2 over 36. So if we apply the additive law to get the probability of getting a 7 or 11, we just add those two probabilities, so your probability will be 0.222. If you think back of part 1, we said that the complement of an event consists of all the outcomes that is still in the sample space but not in that particular event. So if we know the probability of an event, we can get the probability of the complement of that event, since we know that the probability of the whole sample space will be equal to 1. So if we know the probability, for instance, of event A, then we can apply the complement rule, which states that the probability of A's complement will be 1 minus the probability of A. Then just take note that this can also be applicable to conditional probabilities. If the complement of the event is not in the given part, then we can use the complement rule. But if the complement part is in the given part, then unfortunately we can't do that, but we will do an exercise where we will solve that problem. For example, the Bureau of Census states that 50% of all homes in Potchefstroom are heated with gas. Out of 6 randomly selected homes in Potchefstroom, what is the probability that at least one of the homes is heated with gas? Okay, that means that we are looking for one or more homes. We can easily determine the total number of outcomes in our sample space with the multiplication rule first of all. So we did that last week already. Each home will have 2 possible outcomes, and there's 6 houses that we selected. So that means that our total number of individual outcomes will be 2 to the power 6, which will be 64. we can let event A then be the event that at least one home is heated with gas. And then the complement, you can easily see, will only consist of one outcome where none of the houses are heated with gas. So the probability of A's complement will be 1 over 64. So we can obtain the probability of A then by applying our complement law. So 1 minus the probability of A's complement will give us 0.984. The next law is the general additive law, and this law is applicable to events that are not mutually exclusive. So the probability of the union of events A and B will be equal to the probability of A plus the probability of B minus the probability of the intersection of those two events. So why do we subtract that intersection? Because you will basically add it twice, since that intersection will be part of each of the events. For example, let's say in an ordinary deck of cards, we have two events, hearts and kings. Those two events are not mutually exclusive because the king of hearts will both be part of the hearts cards and the king's cards. If you look over here, so we basically add the king of hearts twice, so that's why we need to subtract one of them. For example, students were randomly assigned to 6 different sections of introductory English course, sections 1 up to 6, and events A and B are defined as follows. A is the event that Susan is assigned to an even number section, so that means that the outcomes in A will be 2, 4, and 6, and B, Susan is assigned to a section numbered lower than 3, so that will be the outcomes 1 and 2. The probability of event A will then be 3 over 6, and the probability of B will be 2 over 6. Events A and B have one outcome in common, which was the 2. So the intersection of A and B will be the 2, and the probability of that intersection will be 1 over 6. And now they ask you to find the probability of that union of the two events. Since the two events were not mutually exclusive, we can apply the general additive law. So adding the probability of A to the probability of B and subtracting that intersection, that will give us a probability of 0.667. The multiplicative law of probability use the conditional probabilities formula. So if we know the conditional probability, then we can determine the probability of the intersection of two events. So we basically just swap that formula. So the probability of A and B will be the probability of A times the probability of B given A, or that probability of the intersection will be the probability of B times the probability of A given B. For example, in example 8.21, they state an urn contains 4 red balls and 3 blue balls. 2 balls are selected without replacement. What is the probability that they are both blue? So we can let B1 be the event that the first ball is blue, and B2 be the event that the second ball is blue. If we want the probability of B1 and B2, the probability of B1 will be 3 over 7, since we had 3 blue balls and 7 balls in total. And then if we know that the first ball was blue, then the probability of the second ball also being blue will then be 2 over 6, since you didn't replace the first ball, so your total number of balls will decrease by 1, and if the first ball was blue, then the total number of blue balls will also decrease by 1, so that probability will be 0.143 then. by applying the multiplicative law of probability. Now it's your turn to practice all these concepts so you can complete exercise 14, 13 and 7 of chapter 8, please.